We are going to talk about stoichiometry. Stoichiometry really just means using mole ratios in a reaction to calculate the quantity of reactants and products. So before we have been using mole ratios as well, but we have been using mole ratios to calculate formulas. So we talk about mole ratios of atoms within a molecule. Right? We've been talking about mole ratios to calculate something like the formula of a hydrate. So we would be using like this with 1 as the mole ratio. So we have been using mole ratio, but mole ratio within a formula, so inside a compound. This time though, we're going to talk about mole ratios in a reaction. So what does that allow us to calculate? I'm going to use an example. This question comes from your textbook. It says dinitrogen pentoxide is a white solid. When heated, it decomposes to produce nitrogen dioxide and oxygen. These numbers here, they actually balanced it for you, first of all. But these numbers here, after you balance the equation, is the mole ratio. And a reminder that when you have O2 like this, when there's no number out in the front, it doesn't mean that there's 0 oxygen molecule. It means that there's 1 oxygen molecule right there. What does this mole ratio tell us? In the sentence, it means that if 2 N2O5 molecule reacts, this reaction will produce 4 molecules of NO2 and, at the same time, 1 molecule of O2. But remember that anytime we have a quantity, if we add the word moles to it, it doesn't change anything. So, in other words, I can say that in this reaction, if 2 moles of N2O5 reacts, this reaction will produce 4 moles of NO2 and at the same time 1 mole of oxygen molecule. Okay. Well, what if we don't react exactly 2 moles of N2O5? What if we react another amount? Or what if another amount of dinitrogen pentoxide reacts? So let's copy down this. So this is the same reaction, balanced, so same ratio. What if this time we react, let's say, 5.01 times 10 to the 19 molecules of N2O5. And we want to know how much or how many molecules of NO2 will be produced and how many molecules of O2 will be produced. Well, we know that if 2 molecules react, we can make 4. So the relationship there is times 2, twice as much. But I'm going to put this number in another way. Okay. What if I say times 4 over 2? Well, 4 divided by 2 is 2, so that also means twice as much. Except now you can see where I get those numbers from. The numerator comes from the quantity we want to calculate, and the denominator comes from the quantity that is given. So if you take the quantity you have and you multiply by a fraction, where the numerator is the quantity you want, and the denominator is the quantity you have, you end up multiplying it by 2, and you end up saying that, look, the number of NO2 molecules I will make in this reaction is twice as much as the number of molecules of dinitrogen pentoxide that has reacted. We can apply the same method here and say, well, if we want to figure out the number of molecules of oxygen that's made, all we have to do is multiply by, this is a 1 here, it goes in the numerator because it's the quantity we want to calculate, 1 over 2. 2 coming from the quantity that we already have, that's given. And does this make sense? That you make half as much as what you're given? Well, yes, because it says here, for every 2 dinitrogen pentoxide that you react, you're only going to make 1 oxygen molecule, which is half as much. So this does work. So let's try doing this to figure out this quantity here. So we can take 5.01 times 10 to the 19, multiply that by 4 over 2, and the answer we get is 1.00, 3 significant digits, times 10 to the 20 molecules of NO2. So that is saying that if you react 5.0 times 10 to the 19 molecules of N2O5, you will make 1.00 times 10 to the 20 molecules of NO2. This is twice as much as this quantity here. And using the same method, this time multiplying by a half gives you 2.51, I think, times 10 to the 19 molecules of O2. So that means that if you react 5.01 times 10 to the 19 molecules of N2O5, you will make 2.51 times 10 to the 19 molecules of O2. Yes, so that's right. We can also do this with moles. So same reaction again. 2N2O5 decomposes into 4NO2 plus O2. This time let's work in moles. And let's go backwards. What if, instead of saying how much I react, what if I know how much I want to make? And I say I want to make 7.20 moles of NO2. What does that mean? How many dinitrogen pentoxide molecules do we have to react to produce this amount? Well, using the mole ratio that we learned before, we can multiply by a fraction, and the fraction will be the quantity we want. Let's put a question mark here. The quantity we want, the coefficient is 2, and then the quantity that's given, the coefficient was 4. So we can multiply by 2 over 4. And that is going to give us 3.6 moles. Does that make sense? So what we're saying is that if you want to make a quantity of NO2, you only need to react half as many molecules, 2 over 4, half as many molecules of N2O5. So if you want to make 7.2 moles of NO2, you have to react half as many. 2 over 4 means half as many, so 3.6 moles of N2O5. So I want to emphasize that this step here, this mole ratio, this is a mole ratio step, only works for formula units, molecules, atoms, what else? That's it, I think. But not mass. Not mass. Okay, so we'll work for quantities like molecules, atoms, and moles. Sorry, very important, moles. So these are all counting number of atoms, counting number of molecules, but not mass. So what do you do with mass? So same example. I'm going to write the equation out again so that we have more space. But this time, instead of calculating for molecules or moles, they're asking for grams. Question says, how many grams of oxygen gas, so let's put a question mark, will be produced in this reaction when 2.34, so right here, 2.34 grams of NO2 are made. So they're saying, I don't really care how much of this I'm reacting, but I know that I'm making 2.34 grams of NO2. I want to know how many grams of oxygen is made at the same time. So I'm going to set up a chart that says mass, and it's going to say molar mass, and then the last row is going to say moles. Why do I need moles? Because I know that I can use my mole ratio, which is 1, 2, so 1, because this is a 1 here, 1 over the quantity that I have is, coefficient is 4. I can only use this, but only for moles. Moles or molecules only, not mass. So my master plan is that I can convert mass into moles, then I can use my mole ratio to go across to get moles of O2. Right, so I can go to moles of NO2, I can go mass to moles of NO2, and then I can use my mole ratio to go across and say that's how many moles of O2 I need. And then lastly, if I have moles of oxygen, I can calculate mass of oxygen. So that's the plan, that's the route that we're going to go. So you can see that I also set this up like a chart where my columns, 1, 2, 3 columns are the reactants and products, and then rows, the first row is mass, molar mass, moles. I crossed this out because this column is irrelevant because they didn't ask for N2O5. So let's follow the steps. How do I convert mass to molar mass? You divide by, mass to moles, you divide by the molar mass. And the molar mass of NO2 is 46 grams per mole. 46 grams per mole. So notice that everything I do in this column is about NO2, and NO2 only. So now, 2.34 divided by 46 gives us 0.05087 moles of NO2. And if you make this many moles of NO2, you're only going to make a quarter the amount for oxygen. So that translates to times a quarter gives you 0.01272 moles of oxygen. I'm not saying that these two quantities are equal, so I'm not saying that 0.05087 moles of NO2 is equal to 0.01272 moles of O2. I'm just saying that if you make this many moles of NO2, you will at the same time make 0.01272 moles of oxygen. Now that we know how many moles we can make, we can multiply by the molar mass. So we'll be going up, we multiply by the molar mass of oxygen to get .407 grams of O2, and that is my final answer. Okay, so now we know that if you have a reaction where you make 2.34 grams of NO2, you will make 0.407 grams of oxygen. And we get that by converting grams of NO2 to moles of NO2. Then we use a mole ratio to get moles of O2, and then we multiply by the mass of oxygen to get molar mass of oxygen to get mass of oxygen.